Hello, hello. This is Mrs. Hickman, and today I am going to go over simple harmonic motion. But before I start off with, I want to refer you to another YouTube link. It's going to be Crash Course, and just type in simple harmonic motion. They explain how this works out very, very well with the two-dimensional motion and then the periodic motion. So I would check out Crash Courses Simple Harmonic Motion, and if you're a student, I'm going to attach the video in the link. So I would recommend that you stop and watch that first before you go into this video. Okay, so simple harmonic motion is just talking about a swing bob. It could be a spring bobbing up and down. It could be for like a swing, like if I was starting here, like right here, I start pushing, like I have a daughter and a son, I start pushing them on a swing like this. This is also simple harmonic motion too. So what this does, this is going in a period. So there's a period. It deals with potential and kinetic energy, as you will see in the video. But we're not talking about potential and kinetic energy. We're talking about the calculus behind it. Okay? So let's look at this spring. So just act like that's not there. So let's say we have a spring. This is going to be 0 right here. Okay, 0. This is going to be A, and this is going to be negative A. So yeah, just act like that's not there at all. Here we go. We will make it disappear with blue. Because school colors, yay. Spirit. Anyway, so this is A, 0, negative A. Okay, so say, and this is also going to be time equals 0 as well right here. So time equals 0, so I got a spring, and I'm pulling it down, okay? So the spring is going to bob up and down like this, right? So if I'm stretching it here, right here is where it's, in physics, this is where your potential energy is 0, and this is where your velocity is also going to be at its maximum, okay, and that's where your acceleration is going to be 0. So I'm pulling this down, okay, so S down, velocity is 0, and the acceleration is up. So pull down, it goes up and down, up and down. Right here is rest. Right here is where it's condensing. So you pull a string, it's going to go whoop, like that. Okay, so this is going to be also where velocity is 0 as well. So my rest position, okay, so rest position for, that's just potential, oh, that's potential energy. Okay, anyway, so this is going along the axis, stretch position, rest position, okay, but this is also where velocity is at its max, okay, as you will see later on. Let's look at the math. Okay, so let's say we have a weight that's being stretched 5 units beyond rest position, S equals 0. Okay? And it's released at T equals 0, so S equals 5, bobs up and down. Its position at any time T is S equals 5 cosine of T. I'm getting there. Okay? So what are its velocity and acceleration at time T? Well, that's easy. We just went over particle motion in class. So we know that. So let's do S right here. So S is 5. Other pen. Don't really want to use blue, but it's the only one I see. So here we go. So S equals 5 cosine of T. So it wants us to find the velocity. So velocity is going to be the derivative of that. So velocity is going to be 5 sine of T. Okay? Acceleration is going to be, the derivative of cosine is negative sine, and the derivative, okay, so this is, the derivative of cosine is negative sine, and then this is going to be negative 5 cosine of t. So let's graph this. Let's look what this graph looks like. Okay, so at t equals 0, so this is the S graph. So at t equals 0, it's at 5. So this is the stretched position. I'm going to write one period out. Stretched position, 0, 0. Okay, so that's what the graph looks like. So right here, stretched position, this is when you're seeing, this is where, yeah, this is here, this is where your maximum velocity is going to be. Okay, there and there, okay, which makes sense. So if you're looking at spring, it's down. Right here, it's at rest. Well, S equals 0 anyway. It's changing direction. So it's stretched in the middle, now the whole way up. Okay? In the middle, whole way down. Okay? So that's how it works. So let's talk about the motion of what's going on here. So if we look at this, we are going to see that the amplitude is going to oscillate oscillates. So oscillation just means going back and forth. Oscillates between 5 and -5. And of course this is ignoring friction and air resistance. The period of motion is 2 pi. Okay, now let's graph the velocity and compare it with this. So this is going to look like this. Yeah, pi over 2, using your key points, pi over 2, pi, 3 pi over 2, and 2 pi, 5, -5. So you can either graph it with this or you can just graph it with the sign. So sine of 0 is 0. Sine of pi over 2 is 1, but it's negative, so it's going to be -5. Okay, so let's look at this. So let's see where the greatest speed is. So if I was looking at the greatest speed, that's going to be where I have my max and min values. So if I was to do so, well, before we do speed, let's do velocity. So where's velocity going to be greatest? Obviously, it's going to be when you see a max or a min somewhere. So velocity is greatest at 5 and -5. Now let's look at the other graph real quick so we can compare. Okay. So we see right here, so let's look at the position of velocity. So velocity is greatest when it's here at pi over 2. Okay, so pi over 2 in the position function, that's when it's changing direction. So if we look back at this, or if I ever find the paper again, this, that's where it's crossing. This is where it's crossing the S. This is where you see a velocity, a max or a min right there. Okay? So back here again. Okay, and if we're looking at speed, remember that speed is the absolute value of velocity. Speed is absolute value of the velocity function. So that graph is just going to look like this. It's going to look like an M. So the speed is going to be at 5. So, or you could look right here. So absolute value of 5 equals 5, and the absolute value of -5 is also 5. You could also look at it right there. So that's where your greatest speed and your velocity is going to be. Acceleration is going to act in the opposite direction of the displacement function because gravity is going to pull it in the opposite direction. So gravity will pull in the opposite direction. So we talk about balanced forces. That's what's going on here. So if I did this, it's going to look the exact opposite of this. So instead of 5, it's going to be negative 5 down here. Two pi, 5's here. There you go. Okay, so it's the exact opposite. So it's a force that's acting exactly opposite of the displacement function. So that's what acceleration is doing. One more thing that we will be discussing is a jerk. So a jerk is a sudden change in acceleration. So it changes slope. So there's my spirit blue right there. So a sudden change in acceleration, so there's a derivative. It is caused by a constant acceleration to gravity, or a sudden change in gravity, I guess I should probably say. So, because it was constant acceleration, would be 0. It also explains why we don't experience motion sickness while just sitting around. So, what is the jerk in the previous example, and describe its motion. So, the jerk is going to be the derivative of acceleration, which is going to be 5 sine of t. Okay? And pretty much you're just looking to see where its greatest magnitude of where this happens at. Jerk. Will happen the greatest at or where t equals k pi over 2. Okay, so that's all. That's simple harmonic motion for today. There's your homework. It is going to be on page 146 in the book we're using. If not, yeah. So 11 and 19 on. So have a good day. Bye.